Section 2.2 is on higher degree polynomial functions. In this section, they're going to have you use the equation to determine information about the end behavior of the polynomial function or the behavior around the zeros of the polynomial function. Okay, so the first thing is polynomial functions are continuous, and if they change direction, they have smooth, rounded curves. So for example, maybe it would look like this. It's going to be smooth and curvy. I don't know what it's going to look like. In theory, though, also you could have a linear polynomial function. Then it would just be a line or a constant function. Things that are not polynomial functions, if it has pointy changes of direction like this, that won't happen in a polynomial function. A piecewise function is not continuous. So if it went something like this, even though this is curving, it's not continuous because there is that jump in the middle of the graph. Okay, so the first test they show you about is the leading coefficient test, which indicates the end behavior. So as x approaches infinity and negative infinity, what does the y values of the graph do? Okay, so case one is n is odd, an is positive. So that, for example, n is the degree. So the most basic case of this is maybe y equals x to the third. It could also be y equals x because that has an odd exponent or an odd degree, and the coefficient of the leading term is positive. Okay, if you think about y equals x to the third, the graph goes down on the left and it goes up on the right, which is what we think of as a cubic. Okay, if it's any function with an odd degree and a positive coefficient, it will go down on the left and up on the right, just like a y equals x to the third. Now, what it does in the middle, I don't know what it's going to do in the middle. It depends on the graph and the degree of the graph. Okay, in limit notation, how I would express this. Okay, let's see. I want to say as x approaches positive infinity, so on the right side of the graph, or on the positive side of the x-axis, the graph is going up. The y values are going up. So as x approaches positive infinity, f of x or y is approaching positive infinity as well. What's that saying? On the right side of the graph is going up. Okay, now I'm going to think about as x approaches negative infinity. The order actually doesn't matter though. Okay, so this is on the left side of the x-axis or on the left side of the graph. So I'm looking over on this side. What happens to the y values on the left side of the graph? Oh, the graph's going down. It's going down forever. So as x is approaching negative infinity, f of x is approaching negative infinity as well. So what is this saying? On the left side of the graph is going down. Okay, now the next case is also an odd degree function. They're just saying now n in the coefficient's negative. So maybe I'm thinking of a very basic one to think of. Say I put a negative in front of x to the third. Well, now it's going to reflect. So now it's going to go up on the left and down on the right. Again, I don't know what's going to happen in the middle, but if I just remember it's going to go up on the left, down on the right, I don't know what it's going to do in the middle. It depends on the function. Okay, in limit notation. You can do the left or the right side first, it doesn't matter. Okay, but as x is approaching positive infinity is saying on the positive x-axis side, what's the graph doing? So on the right side, the y values are going down. So f of x is approaching negative infinity. On the right side of the graph, the y values are going down or the graph is decreasing to negative infinity. Okay, as x approaches negative infinity, so on the left side of the graph, what's the graph doing? On the left side of the graph is going up. So f of x is approaching infinity. Okay, the last two cases are when the degree of the function is even, of the polynomial function. So let's see. I normally try to remember a very basic case, and that helps me generalize for all the even functions. So if I think of y equals x squared, that's an even degree function. The coefficient's positive, and that's a parabola where the two sides of the graph, or the two sides, they go up on the left and the right. So that's why it says the graph rises to the left and the right, just like a parabola. Okay, and again, that tells me about the end behavior. This could be x to the 6th, it could be x to the 8th, it could have a bunch of other terms. It might do something crazy in the middle, it might not. But I know on the left and right side, it's going to go up. Okay, so for the end behavior, see, as x approaches infinity is talking about the right side of the graph. On the right side of the graph's going up. Okay. On the left side of the graph is also going up. Okay, and you could rephrase this as kind of like sentences. I could say, as x approaches infinity and x approaches negative infinity, f of x approaches positive infinity. Or f of x approaches infinity as x approaches both infinity and negative infinity. It is like a sentence, so if you read it and it makes sense, then it will work. Okay, the last case is when the degree of the function's even and the coefficient is negative. And again, I just like to think of a basic case because it helps me think of the end behavior a little bit easier. So a basic case would be negative x squared. That has an even degree and a negative coefficient, and I can imagine in my head that's a parabola going down, which is how I know that the graph is going to fall to the left and fall to the right. And again, I don't know what's happening in the middle of the graph. This isn't going to tell me any information about that. Okay, so I'm going to describe the end behavior using limit notation. So as x approaches infinity, the right side of the graph is going down. So f of x is approaching negative infinity. And as x is approaching negative infinity, so the left side of the graph is also going down. Okay, for example 1, we're going to use the leading coefficient test to describe the end behavior of the functions. And there's more than one way to do it to describe the behavior. But for the leading coefficient test, I want to look at the leading term or the highest degree term. So x to the fourth is the highest degree term in the polynomial. The degree is 4. So this is an even degree function. The coefficient is technically 1, so it's positive. So I'm thinking of positive x to the fourth. Since it's even, it's going to go up on both sides, just like x to the second one. So I could do something basic like up on left and right. Okay. If it doesn't tell me a specific way to express that, something as easy as that is fine. If it asks me to use limit notation, I might say, let's see, as x approaches infinity and x approaches negative infinity, f of x approaches positive infinity. It's saying on the right and the left, the graph is going up. Okay, that's one way to do it. I'm going to add a sketch. No, I'll add a sketch of the end behavior right now. Okay, so I do know what's going on up on the left and it's going up on the right. Okay, I'm going to ponder the middle of the graph in a minute, but I'm going to continue first. Okay, so for B, again, I'm only looking at the leading term of the polynomial function, which is the highest degree. So this has a degree of 3, which is an odd number. So this is an odd function, and the coefficient is negative. So I'm thinking this is going to go up on the left, down on the right. Odd has like a mismatch. Okay, it's odd and it's negative, so it goes down on the right. Okay, if I were describing this, you can describe what you see. What does it say? Up, left, down, right, rises on the left, falls on the right. Your book likes to use falls and rises a lot. For limit notation, I might say, let's see, on the left, it goes up, and on the right, the graph goes down. Okay, it's gonna, unless it specifically tells you a way to write it, it's up to you. Okay, and then the last one is f of x equals x to the fifth minus 3x. The leading term is x to the fifth. 5 is an odd number, so this is an odd degree, so it's going to be a mismatch on the end behavior, one up, one down. Since it's positive, it's going to go up, down, something like that. Okay, and again, you can use your own words to describe it. Up, right on the right side, down on the left. Okay, if you wanted to use limit notation or if it asked you to do it, I could say, let's see, on the right, it goes up. On the left, it goes down. Okay, and then we're going to ponder the middle behavior just a little bit. Okay, so it says a polynomial of degree n has at most n real zeros and at most n minus 1 turning points. Okay, so if I look at the first function, this is degree 4. So it could have at most 4 real zeros and possibly 3 turning points, one less. So what's that saying? I'm just going to sketch a random thing. I'm just sketching some random graph. Okay, it's possible that this could be the correct graph. It might look something like this. There's possibly 4 zeros, there's possibly 3 turning points. A turning point is when it changes from increasing to decreasing and vice versa. So this is a turning point, this is a turning point, and this is a turning point. It's possible it could have up to 3 turning points. It might have less. Okay, for this second one, I'm just gonna make up something that might be happening in the middle. It might not be correct, I could be wrong. Since this is a polynomial of degree 3, it might have 3 real zeros. It might have n minus 1 turning points. It might have 2 turning points, which means it's possible that it could go like this, it could go like this, and then there would be 2 turning points, one here and one here. But if you think about x to the third actually has no turning points. So it could be less than 2 turning points, but it will not be more than 2 turning points. Okay, and then for C, this is x to the 5th. There might be up to 5 real zeros. There might be less. And it could have at most 4 turning points, which means it could turn 1, 2, 3, 4 times. 1, 2, 3, 4. It might turn less times. I don't know. I'm just making a guess. And as long as your guess in the middle is reasonable and consistent with your graph, that would be fine. The box below is describing kind of synonyms for the zeros of polynomials. So when f is a polynomial and a is a real number, then if x equals a is a zero of the function, that's the same as saying x equal a is a solution of the polynomial function f of x equals 0, because to find the 0, you set the function equal to 0. It's the same as saying x minus a is a factor of the polynomial, because if I were to factor this and set it equal to 0, I would get x equals a. And it's the same as saying a comma 0 is an x-intercept of the graph of f, because I set the y equal to 0, so a0 would be an x-intercept of the graph of f. Each of these implies the other, so if you know one of these facts, you can assume that what the other fact is also true. Okay, the 0 is still at x equals 2, but with a multiplicity of 5. And if I sketch this, this would actually level off a little bit longer at the x equals 2. It doesn't actually become constant, but it does level off there a little bit. If we're in class, I'm going to show you that on Desmos. If not, you might want to look at it on Desmos. You can see that it does kind of level off a little there. And then also y equals x minus 2 has a 0 of 2. But this is a line, so it passes straight through the x equals 2. Doesn't stop, doesn't pause. Okay, the second case is if there is k is even. If it does, the graph touches, but it doesn't cross the x-axis at x equals a. So what are they talking about? Okay, let's consider y equals x minus 2 squared, because you guys kind of know that's going to be a parabola. It's even function. Okay, so let's say it hits x equals 2. I'm estimating it's there. It's a parabola, so I know the end behavior. It's also even and positive, so I know the end behavior. So it's going up on both sides. Okay. So in this case, the graph touches at x equals 2, but it does not cross the x-axis. It comes back in the way it came from. That's what will happen when it's an even function, an even multiplicity. Okay, let's consider y equals x minus 2 to the fourth. Okay, it's very similar. It's going to be x minus 2 here. It's even, so it's going to go up on both sides because it has a positive coefficient. When you draw this or test this on Desmos, it does come down towards the x minus 2. It actually levels off a little bit at the x minus 2, and then it goes back up. Okay, but look on Desmos and confirm that this is what happens. Okay, for example 2, I'm going to find the real zeros algebraically, including multiplicity, and use what I know about multiplicity of zeros and the end behavior of a graph to make a sketch. And I just want to get the end behavior correct and the behavior at the zeros correct. The rest of the graph I'm not going to worry about. Okay, to find the zeros, of course, I set this equal to 0. Okay, I see there's a common factor. I'm going to take out negative 2x squared, which leaves me with x minus 3. Okay, so I have two zeros. I have x equals 0, and I have x equals 3. Okay, but because the 0 came from this term here, it came from x squared, this 0 actually has a multiplicity of 2. Okay, so when you list them, you might want to list 0, 0, 3, or you can say that 0 has a multiplicity of 2, and the other 0 is 3. Okay, this was degree 3, so I was expecting to get 3 real zeros, which I did. Okay, so I'm going to sketch a graph here. It's just a graph, but I know there's a 0 at 0, 1, 2, 3. Okay, let me consider the end behavior before I start sketching this. Okay, if I look at the leading coefficient or leading term, it's an odd leading term. So it's going to go up on one side and down on the other. It's negative, so it's going to go down on the right and up on the left. Down, right, up, left. And you do not need to list it unless it tells you to, but I'm going to keep that in mind for when I'm graphing it. Okay, I know there's a 0 at 0 and 3. Okay, now let me think about this. Okay, I know that it's going to go down on the right. So from the 0, I know it's somehow going to go down. I don't know which way it's going to go down, but it's going down. I know it's going to go up on the left. So somewhere from this 0, it needs to go up. Okay, and this is just a sketch. Okay, now what's going to happen in the middle? I'm just going to make a sketch based on the zeros and the multiplicity of the zeros. Okay, because x equals 0 has a multiplicity of 2, this is even. It has an even k. Okay, so this graph is going to hit at 0, but it's not going to pass through the 0. It's going to come back up. Okay, because the x equals 3 has a multiplicity of 1, that's odd, and it's going to pass right through. Okay, so this is a decent graph. It is going down on the right, up on the left. Because the x equals 0 had a multiplicity of 2, it bounced back up from the x equals 0. Since the x equals 3 had a multiplicity of 1, it passed straight through it. Okay, and as long as it's respecting the behavior at the zeros and the end behavior, that's a reasonable sketch. Okay, I'm going to do the same type of thing for the next one. It does have a fraction because some of you don't like fractions. Okay, first I'm going to find the zeros, and then I'll consider the end behavior and any multiplicities. So let's see, I'm going to definitely take out an x. I'm also going to take out a half x to get rid of the fractions. Okay, half x times x squared gives me 1/2 x to the third. Let's see, half x times something to give me x squared is actually going to be 2x, because half of 2 is 1, and x times x is x squared. Okay, and then the last one is just going to be 3, because if I do half x times 3, I get 3 halves x. Okay, and this is really just to make it easier for me to factor. Okay, let's see, I got x equals 0, x equals 3, x equals -1, and this was a polynomial function of degree 3, so I was expecting it to get 3 zeros, and I did get 3 zeros. If you want to consider the multiplicity, these each have a multiplicity of 1, since there's no exponent listed there. But knowing the zeros already gives me a good start on my sketch. Okay, let me consider. I'm going to have a 0 at 0, +3, and -1. They all have multiplicity 1, so I know it's just going to pass through. So I'm going to consider the end behavior before I progress. Okay, the leading term is 1/2 x to the third. Since it's odd, it's going to go up on one side, down on the other. Since it's positive, it's going to go up on the right, down on the left. And again, you don't have to write it, but your graph needs to reflect that you respected the end behavior. So it's going to go up on the right, down on the left. Okay, now in the middle, it's got to pass through each of these zeros and only these zeros. There should not be any extra zeros going on. So it's going to do something like this. Okay. I didn't label my y scale because I'm not going to worry about the actual points. It's respecting the end behavior, and it's respecting the behavior at the zeros that I was expecting. So this is a good enough sketch. Okay, for the last example, they're giving you the zeros, and they want you to write a polynomial function in standard form that has the given zeros in standard form or general form. Okay, there are infinite number of answers. I normally go for the most basic possibility just to make them, because I have to multiply this out, it'll make it a little easier. Okay, so I'm going to consider this function. You could say f of x equals, g of x equals, y equals. Okay, if the first zero is -2, then it must be true that x plus 2 is a factor. Okay, for the next zero is 5. For 5 to be a 0, it is also true that x minus 5 must be a factor. Okay, and then for the last 0, -5 must mean that x plus 5 was a factor. Okay, this is not a unique polynomial function. I could have had 2x plus 4 to get x equals -2. I could have had many other ways, but to make my life easier, I'm going to go with the most basic one. Okay, because they want it in standard form or general form, they actually do want you to multiply this out, which means you could have a different answer. Okay, I need to multiply all of these out. Sometimes there's a pair that are easier to multiply, and if you do them first, it makes it easier. Okay, so I'm actually going to multiply these out first because I can do that in my head. The order, though, does not actually matter, but I can tell this is a difference of squares. So that's going to be x squared plus 5x minus 5x cancel minus 25. Okay, and then I can distribute these two binomials out. What is that? X to the third plus 2x squared minus 25x minus 50. Okay, and you could have multiplied it in a different order. If we have the same factors, we should end in the same one. And this is what we're going for if they say general or standard form. They want it multiplied out. Okay, we're going to do one more like that for this section, and then we'll be done. Okay, and again, these are non-unique polynomial functions, so you could have another function that's just as correct, and I will try to mark it correct. Okay, now this part B has two zeros, 3 plus √5 and 3 minus √5. Okay, so let me think about this. To get 3 plus √5 as my answer, then I must have x minus 3 minus √5. Okay, and then if I think about that, if I were to solve that, I would add the 3, I would add the √5, and I would get 3 plus √5. Okay, for the second factor, to get this as an answer, it would have to be x minus 3 plus √5. Because if I solve this, I would add the 3 and get a positive 3, and I would minus the √5 and get a minus √5. Okay, now there are two ways to multiply this out. One of them is just brute forced. One of them is noticing that this is a difference of squares. I'm going to show you both ways, and you're going to use whichever way gives you the answer correctly, is most accurate for you. Okay, the first way, I'm just gonna do it. I'm just gonna multiply every single term out till it works out. Okay, so I get x squared minus 3x plus root 5x. Okay, then I'm going to do the minus 3, so minus 3x. What am I getting? Let's see if I run out of room. Minus 3x plus 9. I'm going to continue on the next line. Minus 3 root 5. And then what's left? Minus 5 root 5x plus 3 root 5 minus 5. 1, 2, 3, 4, 5, 6, 7, 8, 9 terms. Okay, this is going to turn out nicely at the end. So look for things to cancel. Those cancel. These cancel. Okay, so let me see what's left. I get f of x equals x squared minus 3x minus 6x, and then 9 minus 5, positive 4. Okay, so this is a polynomial function that if I solve for the zeros would give me those two answers, and I could always verify that that works. Now, obviously that was a lot of work when there's actually a pattern in this. So let's consider this again. Okay, and you can always do it the long way. It will work. But sometimes we want to look for a pattern to make it easier. Okay, I'm going to consider the fact that these are almost the same factors. They both have an x minus 3, and then one of them has a minus root 5 and one of them has a plus root 5, which really means this is a difference of squares. And if I consider it like that, then when I multiply this out, I'm really getting the first thing squared minus the second thing squared. Because this is really x minus 3 squared minus root 5 squared. This will be x squared. Make sure you multiply this all the way out. Plus 9 minus 5 x squared minus 6x plus 4. So I get the same polynomial function. But if you notice the difference of squares pattern, it makes it a little easier to make sure you're getting a more accurate answer.